just gonna be a small quickie or a real quickie because I'm doing this in the morning before I'm being fetched by the bus. So yeah, this video is gonna be relatively short. It's just a footnote before we discuss further things in algebraic Femboy theory. What I'm gonna discuss in today's lecture is a couple more structures or Femboy structures that we can construct, or a femboyization of some additional structures. Okay, so you guys know S1 already, okay, right? You guys know S1, it is the circle, or it is at least the unit circle. X squared plus y squared equals r squared, such that the triplet x, y, and r exists in R3. Okay, yeah, we have S1. It has no area. It is just this thin, this infinitely thin ring of points or set of points that's up to look like a circle. That's S1. S2 is the unit sphere. Y squared plus z squared equals r squared, such that the quadruplet x, y, z, r exists in R4. Okay, so that exists in R4. So it would look something like this. S3 of course contains 4 coordinates now. That's the hypersphere in 4 dimensions. But actually all of these fall under the term hypersphere of n dimensions. So this is of 1 dimension, of 2 dimensions. And it rings true with our notion of dimensions in the sense of topology, because when we talk about dimension in the sense of topology, the first dimension is usually a curve. It's a curve. The 0 dimension is a point. S0 is just, nothing, it's just 0. S1 is a curve. S2 is a surface, as we remember from topology. S3 is some tesseract-like surface, that's a sphere. So if we think of these as like built from cells, I believe, n cells, this would be built out of an infinite, infinite identifications of 1 cells. This would be made out of infinite identifications of 2 cells, and then the S3 would be infinite identifications of the 3 cell. So this would be infinite identifications of a line. This would be infinite identifications of a sheet. So if you think about it, this is built from a line. You just grab a line and then you connect the ends by identifying them to be the same point, right? Now here, what we do is morph, or we identify the 4 vertices of a sheet of paper, or maybe even just a square. We identify those to be the same point, zip up the remaining holes, and then bulge it out into a sphere. That's what we essentially do to construct S2. Another way of constructing these things is by taking quotient groups, most notably between the complex numbers. So this is actually homeomorphic to C mod the Gaussian integers. That will come at a later lecture, a different footnote. Okay. So to femboyize this, what we just do instead is to think of these points not as points themselves, but as abstractions of femboys. So we think of x and y here as components, you could say, of a femboy vector in R2. While this one here, we think of them as femboy vectors that satisfy this equality in R3. Now the only reason why I'm saying that x, y, and r is in R3 because it's a triplet of points. S1 is essentially a function that sends the points x, y, r to this relation. So instead of thinking of this just as a set, we can think of it as a relation. So S1 maps R3 onto this relation space. It's an R2 space. And now, the only reason why I'm calling this R3 is not that the space itself is inherently 3-dimensional, but instead we take 3 distinct outputs x, y, and r. So x, y, and r are taken under S1, or the map S1, to the relation x squared plus y squared equals r squared. And likewise for S2, S2 maps R4 onto R3. So any spherical map Sn sends, or any sphere map of real components or real sphere maps 2n dimensions. Not really that. Maps n dimensions, right? Oh no, it's 2 S2. This is R4. So you have 3 components. This is S1, 3 components. N plus 2 dimensions onto R to the n plus 1. So it maps n plus 2 dimensions onto n plus 1 dimensions. So if we somehow find a way to package this into a matrix, if we somehow manage to package all this into a matrix, the rank of our matrix would certainly be n plus 1. The rank of the matrix would be n plus 1. So the space of our image or our images would be that. Okay? And then this one here is just, x, y, z, and r is taken to the relation x squared plus y squared plus z squared equals r squared. We can generalize all this. So S2. We can generalize all this stuff by saying an S to the n map is equivalent to the relation or the set, the sum under I of any coordinates, or the square of the coordinates x of I, where x of I are the individual index coordinates that would satisfy this relation, would be equal to some constant r, small r, some constant small r, such that this index set is contained, this index set and r are contained in the real numbers. Or if we let this range over some value 1 to n, this would be there, and then r would exist in r to the n plus 1 dimensions, r to the n plus 1, and I exists in the interval 1 to n, or is indexed by an interval I, and then we just say that I is equal to this interval. So that's our generalization of a spherical map. So like I said over here, Sn maps R to the n plus 2 space onto R to the n plus 1 space. And okay, so let's femboyize this. What we have to do is just put an F in front of this and then say that these 3 things are femboys. So we're trying to find instead femboys such that our intuitive notion of multiplication or exponentiation and addition carries on over. So when we femboyize this and say that instead of R3 it exists in F3, we assume that the structure of addition and multiplication, most notably exponentiation, carries on over from R. So let's femboyize it. So to femboyize it, what we have to do is instead say that this exists in F3. Now I don't need to change the coordinates anymore, I just need to change the domain, or where these guys inherently come from. So instead, it now maps, instead of R, it now maps F to the n plus 2 space onto F to the n plus 1 space. And F to the 3 space and F2 space. F4 space up to F3 space. Okay. And just so you know, even though we femboyize these maps, they would still hold the same rank if we were to package them into a matrix, or if we were to find some matrix, even though it's non-linear or some shit like that, and apply it on our thing, our dimensions would still remain n plus 1 for a given s to the n map. So we can think of the sphere as not just a set of all points that satisfy this crucial relation, but we can also think of it as a map from one space to another. Okay, that's cool. But we're only considering an infinitely thin ring of points here, and here an infinite shell of points or sphere points. We're not taking into consideration the area and the volume respectively. So what if we take into consideration the area, or just talk about the area inside here, or just the volume inside of here? Well, we're now diving into the notion of a disk and a ball. Now, the ball and the sphere are two separate things in mathematics, because when we talk about the sphere corresponds to the boundary, while a ball implies or is correspondent to the volume. And there is a crucial relation between the sphere and the ball. But notably speaking, there are two types of balls that exist in mathematics. There is the open ball and there is the closed ball. Now the open ball, actually before we discuss about the sphere and the ball, let's first talk about the disk. Now the disk is a bit of an abstract term, but it is basically just the area inside of a sphere. So the relation for a disk, so a disk, D2, as we call it in topology, is the map, or I'll talk about the map later, but it sends the points x squared plus y squared, but instead sets them less than or equal to r squared. And then of course x, y, and r exists in R3. So the input space is 3-dimensional, but our output space is 2-dimensional. Okay, so this is a disk. Well, it's a closed disk. D2, we denote the open disk as the interior of D2, which is just this same exact relation, but we don't set it equivalent to r squared. Okay, so this is an open disk. So which is regular disk and an open disk. Now the interior, the open disk, has no boundary. But the boundary of D2, a closed disk, is precisely S1. Or it's not precisely, it could possibly be S1, but we can say it is homeomorphic to S1. Because when in topology we don't directly say that something is equivalent to another until we have proven or shown that that equivalence relation is precisely what we say it is. So until further notice, when we have two things that we think are the same, or we know that are the same but we cannot prove it that are the same, we just say they are homeomorphic. So this D2 is homeomorphic to S1. Okay, so this disk, if I were to draw it here, this is an open disk. Now the reason why I'm saying I'm using a dotted line because the boundary doesn't exist. I know the notion is a bit confusing, or is a bit it's a bit weird or strange because we don't have a boundary to bound this. How are we to tell that this is a circle, right? Well, of course, because it satisfies this relation. It is simply less than r squared. So this boundary over here would be r, and so it's less than that. So all points that are like that, or that are all like that. So it follows some rules of trigonometry, and that's what matters. Now the closed disk is just S1, but shaded in. It's just S1, but we have points inside it now. Because primarily S1 contains no points inside it, it's just that the thin ring over there. S1 is its own boundary, okay? So the boundary of Fs1 is simply just Fs1. It's its own boundary. It doesn't have an area, neither is it an area type deal, but it is, yeah. And this makes sense Because in the traditional notion of curves here, curves inherently don't have area. Area is a strictly two-dimensional thing, but the best way to think about it is that if you were to stand over here, precisely on the surface of this disk, you'd be able to see the stuff around you as two-dimensional stuff. But if you were to stand on a one-dimensional curve, all you would see is a line that extends forward, and of course it's gonna curve. Though that's sort of the best way I think about it, why dimensions are what they are. Why this is 2D, and it makes sense too because it's a two-dimensional thing. But this is inherently a surface, and not just a curve, because we have area here, because a curve is only just itself, doesn't really have area. Now FD2, to femboyize it, the open and closed femboy disk would just be, we just say that X, Y, and R exist in F3. So it's FD2, and then this is the interior of FD2. And the boundary of FD2 is FS1. And the interior, the boundary of the interior of this one doesn't exist. And that makes sense because the interior should never have a boundary, right? Because it is the interior is inherently an open thing. Now you can probably define some interior that has a boundary, but then that would just be the entire shape. So it's, if I have some irregular blotch of femboys and take its interior, that would inherently, by the definition of an interior, exclude the boundary. Okay, so now we talk about the disk. This is the femboy disk. Open and closed femboy disk. This is the open femboy disk, this is the closed femboy disk. Let's talk about an important or crucial relation between the sphere and the ball. Okay. So there are two types of balls, an open and closed ball. And the notation is the same as disks. But we denote ball this time as B3. I know this breaks with our notion of surfaces, but the only reason why we call it B3 is because we have three components here to describe it, because a ball is a three-dimensional object, in the sense of geometry, not topology. A three-dimensional object in the sense of topology would be a tesseract, or a four-dimensional object in the case of geometry. It's a bit confusing, but this is just how the notation is. So B3 is the volume of the sphere, or the volume enclosed by a sphere. So this is x squared plus y squared is less than or equal to, there's a z squared. The z squared is less than or equal to r squared. And then all these exist in a four-dimensional spacetime. X, y, z, r in R4. Okay. And then the open ball is just its interior. And then,